Got this cool video that'll help explain this. I love the music in this one.
This is a gyroscope. It consists of a metal wheel mounted on an axle. The wheel and axle spin freely, secured in a metal frame. This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try to suspend it like this and it drops. Apparently it can't defy gravity. But spin the wheel and all that changes. A string provides a simple method to spin the wheel. The first thing I notice about the spinning gyroscope is that it resists attempts to change its position. A resistive force appears when I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning wheel is creating a force that holds the gyroscope upright. When the wheel stops, the force disappears and the gyroscope falls. Incredibly, this force will support the gyroscope like this. It appears to be levitating. A spinning gyroscope will balance on a string. You can even lift the gyroscope with a string looped around one end. This interesting behavior is difficult to explain. Physicists have determined that a rotating wheel has angular momentum, similar to the momentum that a stone flying through the air has. To change the direction of the stone requires a force. Similarly, changing the orientation of the rotating wheel requires force. The spinning wheel prefers to stay oriented as it is, and it resists any attempt to change that orientation. The fact that gyroscopes will maintain a particular orientation in space is very useful. In modern aircraft, an inertial guidance system uses spinning gyroscopes to monitor and control the orientation of the aircraft. The gyroscope is suspended in a special cage that allows it to maintain its orientation independent of the aircraft's position. If the aircraft rolls, electric sensors and contacts connected to the gyro send information to the pilot about the aircraft's orientation. The Mars rover explores the surface of Mars using spinning gyroscopes to provide stability and navigational information. This full-sized robotic helicopter flies without an onboard pilot. Gyroscopes provide stability and navigation. Gyroscopes have become essential components of aircraft, ships, robots, and spacecraft. If you're interested in experimenting with a gyroscope, they are available from online science and hobby retailers. The gyroscopes I am using are manufactured by Tedco Manufacturing in Hagerstown, Indiana. They are identical to toy gyroscopes first manufactured over 90 years ago. More science and technology related videos can be found at our website, hylaroad.com. Follow the project's link.
So the original mechanical gyroscopes worked by the conservation of angular momentum. The spinning disc resisted the change in orientation caused by any of the external torques, and hence the orientation of the gyroscope itself, the spinning disc, would remain nearly fixed regardless of the motion of the platform. You can then get the orientation by measuring the angles between the adjacent gimbals. So for example, in the video, as the plane moved around, you could measure the relative orientation of these gimbals to say, well, the plane must be pitched this way or yawed this way. But how do we do it now with our inexpensive MEMS devices? Basically what we do is we take a couple masses here and we make them oscillate with known frequency back and forth, and we note that the rotational rate that we're trying to measure will yield a Coriolis force within the coordinate frame. So note that the masses are being forced to vibrate back and forth this way, and if this whole device gets rotated, there will be a Coriolis force associated with it. Now that Coriolis force can actually be measured by looking at the deflection of those masses, assuming of course we know the spring constant, and then we can take that Coriolis force and plug it in to our Coriolis force equation, which is the cross product of the rotational rate and the velocity. Now, as I mentioned on the last slide, we're setting the velocity and we're trying to find the rotational rate. So as long as we know the mass, which we do because we built this, we can actually back out this rotational rate. So measure the Coriolis force with the deflection, plug it in with these other known variables, and we can back out the rotational rate. The last sensor that we use takes advantage of the Earth's magnetic field. Here's another video. I love these promo startups.
Hello, Dan Elski here from howtomechatronics.com. In this video, we will learn what is Hall effect and how Hall effect sensors work. The Hall effect is the most common method of measuring magnetic field, and Hall effect sensors are very popular and have many contemporary applications. For example, they can be found in vehicles as wheel speed sensors, as well as crankshaft or camshaft position sensors. Also, they are often used as switches, MEMS compasses, proximity sensors, and so on. Now, we will go through some of these sensors and see how they work, but first let's explain what is the Hall effect. Here's the experiment that explains the Hall effect. If we have a thin conductive plate as illustrated and we set current to flow through it, the charge carriers would flow in a straight line from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we will disturb the straight flow of the charge carriers due to a force called Lorentz force. In such a case, the electrons will deflect to one side of the plate and the positive poles to the other side of the plate. This means if we put a meter now between these two sides, we will get some voltage which can be measured. So, the effect of getting a measurable voltage, as we explained above, is called the Hall effect, after Edwin Hall, who discovered it in 1879.
So using sensors like the Hall effect sensors, we can actually measure the Earth's magnetic field, which is great. It gives us a sense of direction. Now there's a couple things to note here. The first is that there are 3 dimensions going on here. But the next is that we're going to get different magnetic fields being measured at different parts of the world. You're going to have different strengths, and you really need to be careful of that. Now here's one way to take 2 different Hall effect sensors or magnetometers that are orthogonal to each other, so that you might be able to determine whether your IMU is facing in the north, south, east, or west direction. What you'll notice is that if you hold your IMU sort of level with the Earth, you've got your X and Y facing magnetometers, and you use those 2 signals, and you'll notice that they're going to be out of phase by 90 degrees. And by looking at the 2 measurements, one from the X and one from the Y, the combination can be used to determine your actual heading. That is, if you have a very strong value with your Y measurement and 0 with your X measurement, then you're facing east. If you have a very strong negative X magnetometer measurement and 0 measurement from your Y, then you're probably facing south.